Hi, everybody. So this video is Blue Part 1. This is where we're going to talk about free fall problems and the physics that we're going to do with free fall. So first, when we say that we're talking about free fall, what do we mean when we say an object is under free fall? So free fall, we're going to make the assumption that the acceleration that the object is experiencing is g, 9.81 meters per second squared. The acceleration due to gravity, I guess that can change depending, because we'll have some atmospheric problems where it's not 9.81, but it's g. Free fall meaning you're free of air drag. The only thing causing you to move is gravity. So that's going to be important here. That means that we're free. Whoops. Free of air drag. Now, let's look at a couple examples. We'll look at the image on the left in a minute. So, a message for President Trump is dropped from some height above the ground. If in free fall, how much will the object's velocity change each second during its descent? So we're trying to find the change in velocity over time, right? So, and I'll do this below here. We have change in velocity. That is just acceleration times time, or you can say delta x over delta t, right? But we want to know how much. All we know that it's dropped from some height, right? And we want to know every second. So time is going to be 1, right? For 1 second, how much did velocity change? But we don't know the distance, right? It just says some height above the ground. So what we do know is that it's in free fall. Free fall means acceleration is 9.81. So we know that it will not be delta x over delta t. Whoops, what's happening? There we go. So we know that the acceleration will be negative 9.81 meters per second squared, and that will be times 1 second. So the delta v will be negative 9.81 meters per second. That means that the velocity will be changing. It will decrease by 9.81 meters per second in that 1 second. So every second, it will be changing by 9.81 meters per second. That's basically the definition of free fall, right? Let's move this. I'll move you over here. Now, a student on a building of height h throws one ball upward with an initial velocity of v naught and another ball downward with the same speed. Compare the final velocities of the two balls when they hit the ground. Hint, see the figure. So let's look at this figure real quick, shall we? We have this student on top of a building. And then they actually have some information here for us. Let's grab a pencil. So initially we have, okay, so y is 0, t is 0. We start off at 20 meters per second, and the acceleration is negative 9.80 meters per second squared. Now, if he throws it up, oh, nope. There we go. No. Okay, maybe I just need to use my finger. There we go. So he throws it up. It peaks at 2.04 seconds at 20.4 meters. That stuff we don't really need to know. But our hint here is that at the peak, we have a velocity of 0. That's important. Then when the object returns, the height is 0, back to the same height that we started at, but now the velocity is negative 20 meters per second. That's implying that when you throw something up, when you return back to the same height that it was thrown from, you have the same speed, but in the opposite direction. Then as we continue going, then at part D, we are actually exceeding the 20 that we had there. So if we change this scenario a little bit, right? The student is on a building of height h, throws one ball upward with v naught, and throws another ball downward, also with the same speed, not the same velocity, right? So let's say he throws with 5 meters per second up. The other one is a negative 5 meters per second down. Compare the final velocities of the two balls when they hit the ground. So if let's just draw this real quick. If this ball is thrown up with an initial velocity v naught, ball 2 is thrown down with a velocity of negative v naught, right? Same speed, but opposite direction. When ball 1 comes back down to start its downward journey from that level, it will also have the same. It'll now have negative v naught, as we saw up here. When a ball is, when a ball is thrown upward with a velocity of 20, when it returns to that same spot, it will have the opposite velocity, right? Same magnitude, opposite direction. So instead of positive 20, it's negative 20. So if we go back down here. Okay, so ball 1 and ball 2 are both traveling downward from this starting point here with a velocity of negative v naught. So assuming that they're all in the same gravity and have the same acceleration, because acceleration will equal g, which, depending on who you're asking, is negative 9.81 meters per second squared. They will then have the same v final, right? So v final of ball 1 will be the same as v final 2, because they are leaving this spot, traveling downward with the same velocity, negative v naught. So then they will arrive with the same final velocity as well. Now, the time would be different, right? If ball 1 is thrown at the same time as ball 2 will hit the ground much faster, because ball 1 has to go up first and then back down. So yes, they'll have the same final velocity. They won't have the same time, but they will have the same final velocity. 2.20 constructing trios. First, we're given this little table with two scenarios, scenario A and scenario B. Okay, and these are given to us as free fall scenarios. Okay. We have an initial velocity in scenario A of negative 5 and initial position of 20 meters. Then in scenario B, we have an initial velocity of 7 meters per second and an initial position of 15 meters. Now, we are going to graph these two free fall scenarios as trios. You guys did trios with ASCII. A trio is where you graph the position, velocity, and acceleration, and you can see the relationship with them. And as we start using more calculus, we'll see that that relationship is easy to bounce back and forth with. However, free fall is giving us our given right off the bat, that is negative 9.81 meters per second squared for our acceleration. So we already have that information going forward. So let's call this our x versus t, our b versus t, and our a versus t. Now we have constant acceleration to use these kinematics, right? Now we, if the acceleration is constant, we know that it is negative 9.81. We can bust out a ruler and just give us a negative acceleration there. Bingo. So we will call that negative 9.81 for our acceleration, because it is going to be a constant acceleration under free fall. Now that we have that information, we can determine velocity, right? Now velocity is going to be linear, right? So if we have a trio, right? If acceleration is constant, velocity is linear, and position is parabolic. That is only in a constant acceleration scenario. But this is the natural progression in math as well. If you're going to increase the complexity of your graph by increasing the exponent of the line. So constant has no variable, linear has a variable, and parabolic has a variable squared. So if we're going to go from constant to linear graph over in velocity, we know some information. We have an initial velocity of 5 meters per second, negative 5. And we know that the slope of that line is going to be our acceleration. We talked about that before, how the slope of velocity will give you acceleration, or the slope of position will give you velocity. So let's say that if that's negative 5, let's say that's negative 10 at 1 second. I'm just eyeballing that, so don't quote me on it. But we are going to connect those two lines right here. Bingo. Get rid of the ruler. So that is going to be our velocity line. Now, you don't have to include the negative time on your velocity line because we don't know that there is a negative time scenario in this physics problem, but that is the graph that we would use. Now for the position. We do have initial position. We have 20 meters as our initial position. It already has a negative velocity, so it wasn't dropped, it wasn't thrown upward, it seems to be thrown downward or mid-flight downward. So that means that we will connect a negative parabola at that 20 meters. Now we can find the time. The time can be found if we use the blue quad. We're going to get to the blue quad in a bit. But before we do that, I will say that the time that we get here time is 1.57 seconds if you put that into your blue quad now. So that means that we go over about 1.5. I'm just guessing here. 1.57 seconds. And that's already going to be mid-parabola, okay, when it drops. So that means that our initial slope needs to be negative 5. Okay. The velocity at any given point should be the slope of the position at any given point. And you can see very quickly on the velocity graph that that slope is getting further and further negative as we go. So not the prettiest graph, but the graph that we've got. Okay. All right. Now let's go back up and check out scenario 2. Scenario B says that we have an initial velocity of positive 7 meters per second and an initial position of 15 meters per second. So let's go back down. We know that the acceleration will be negative 9.81 because it's free fall. So we have, oh, whoops, I stole an eraser. X versus t, v versus t, and acceleration versus t. And again, we will have constant acceleration, linear velocity, and parabolic position. So let's put our constant acceleration down there. Constant acceleration of negative 9.81. Then our linear, we know we have an initial, now our initial velocity is positive, so that is going to be positive 7 meters per second. So we will have the same slope as last time. It is just going to be from a different starting point. So let's get that ruler back up. Again, don't quote me on this slope. This is all approximate. There you go. That's not bad. Okay, so that's what our slope's going to look like. In parabolic position, we have an initial position of 15. So it's 15 meters, but our initial velocity is positive this time, meaning that the object, we don't know it's a ball, I was going to say ball flying up. The object flying up is traveling upward before it reaches a peak and falls downward. And if you're to do the blue quad, you can do this. You would just need to plug in your givens. I'm not going to do that here to save some time. T is 2.60 seconds. So if we go over, let's call that, I know this is not to scale, but let's call that 2.60 seconds. So we need to go up and then down. And I missed. Let's see. You know what? Let's get rid of that dot. Let's just say that whatever I draw is going to be 2.6 seconds. There we go. So it goes up, has that sloppy peak that I drew up there, but it's going to start with an initial velocity and then come right back down. Okay, so two different ways that we can show that, but they're both going to be a parabolic downward curve because they are in free fall. Okay, so first we graphed the two free fall scenarios above as trios. So what does a negative velocity tell us about direction? Well, negative velocity is traditionally defined as going left, going backwards, or in the y direction going down. So our initial velocity being negative in scenario A, we knew it was free fall. We made the assumption that it was purely in the y direction, so we knew that the velocity was going down. Now, what about a negative acceleration? This gets a little trickier. Okay? So this could mean that you've got a positive velocity that's slowing down, or you've got a negative velocity that's speeding up, right? However, in both cases, v is decreasing or getting more negative, or getting closer to the negatives, however way you want to think about it. But negative acceleration doesn't always mean slowing down. It doesn't always mean that you're going down, right? On scenario B, if we look here, there is still negative acceleration right here. Negative acceleration in that area, but the object is still going upward. It's just slowing down. And then it's going to pivot right there at the top point. And then it's going to start going downward. And if these lines were accurate, then that point would be the same as that point where velocity equals 0. And it's kind of close. So negative acceleration can mean different things in different scenarios. Now, write the free fall kinematic equations here. So let me erase this real quick, and then we will get those free fall equations. All right, so now we'll write the blue equations here. I'm not going to use the blue equations when we do our problems. I'm going to stick to the orange equations and adapt them as we go. Uh, and in the next slide, I'll talk more on that. But for simplicity's sake, if you want to use the blue equations, I will give them to you here. So we start with V final in the y direction is V naught in the y direction minus GT. Okay. Next to blue equation, you've got delta y equals V naught y t minus, not plus, minus 1/2 GT squared. And then the last one is, that turned right over there, is V final in the y squared equals V naught in the y squared minus 2g delta y. So those are the free fall kinematic equations. I am not going to use them in this form because, like you saw, I keep getting tripped up by the negatives. G can be confusing, and the y change we can do simply by changing the x to a y in an orange equation. But anyway, let's get on with the next slide, and we'll talk more about that. So, what is the relationship between the general kinematic equations and the free fall kinematic equations? So, orange versus blue, right? So, the real differences here. Okay. Oh no, I lost my orange. So the real difference here is that orange, you use acceleration, but for blue, you use g. Now, the other issue is that you also have a negative on that g, which is confusing, just like you saw me screw that up already. Also, in the orange equations, you use delta x. In the blue equations, you use delta y. That's not an issue on that substitution. But here, this trips up a lot of people and can sometimes cause unnecessary confusion. So I will stick to the orange equations because in a free fall, we know that acceleration is negative 9.81 meters per second squared. Now, g equals 9.81 meters per second squared, but then you also have to say that it is downward and throw in that negative. Whereas if we just stick with this as our given, we don't have to make any variable changes, and we don't have to change any signs in the equations. Then we don't have to memorize a whole other set of equations, orange and blue, right? So I will be using orange from here on out. And the reason why, not just because I'm super forgetful on my signs, but also because of the answer to this next question. The answer to the next question, number 2, have you noticed which set are on the AP equation sheet? The AP equation sheet can be found on our website on Canvas, and it's just freely available on the College Board website. That's why I want a pen. So the orange equations are the only ones that show up on the AP equation sheet. At the end of this class, I'm hoping that all of you are taking the AP test, but I also want you most prepared for the AP test. And if you can do your free fall problems with just orange, then you're good to go with just using this equation sheet on your test. And then you're more familiar with those equations. I don't want you guys to remember that, okay, so this is how I convert orange to blue, and then I can use my blue equations, things like that. It just gets tricky, and it takes up time. I think that it's easier to just stick with the orange. Now, the quad in each of these kinematics, there's 3 traditional kinematic equations. The 4th one is what we call the orange quad or the blue quad. For number 3, we're going to derive that. So the quad can be derived from the position equation. Delta x equals v naught t plus 1/2 at squared, right? Now this looks like a quadratic, right? To solve a quadratic, you have to get everything equal to 0, right? So let's subtract our variables over here. I don't know how you guys like your algebra, but I like the highest exponent first. So we have 0 equals 1/2 at squared plus v naught t minus delta x. Now, if we want to solve this, usually when you have a quadratic, you're solving for x, right? So say you've got 3x squared minus 6x plus 4 equals 0, you can solve for that using the quadratic equation. So in the quadratic equation, this is a, this is b, this is c. So you use the equation x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Now this gets really confusing because we have an a in our equation. But this 1/2 a is a, v naught is b, and negative delta x is c. Just like up here, 3 is a, negative 6 is b, and 4 is c. So let's scroll down and let's follow that pattern to make a quadratic. So we are solving for t. This is the only equation that actually solves for t in the kinematics. You can solve the other one. Which one is it? Oh yeah, v final equals v naught plus at. This is how you can solve that one for t. But if you don't have v final, which is common the problem, which is why you would use this. V final is missing. If you don't have v final, then you can't find t using one of these traditional equations. So you have to use the quadratic. So let's see. We start off with t equals negative b, which is negative v naught, plus or minus the square root of v naught squared minus, what is it, 4ac? Minus 4 times our a, which is 1/2 acceleration, times our c, which is negative delta x, all over 2 times our a, which is 1/2 a. Told you that a is going to get silly. So let's simplify that. The negative times negative becomes a positive inside there. So we've got t equals negative v naught plus or minus the square root v naught squared plus, because you got minus times minus is plus. Then you've got 2a delta x all over 2 times 1/2 is 1 all over a. So that is the orange quadratic. Orange. Orange quad. Now, if we convert that to blue, things get messy. Because remember, everywhere you've got an a, that's got to go to negative g. Anything you've got a delta x, that's got to go to delta y. So your blue quad, if you choose to use blue, whoops, why did that, oh, whoops, hit the wrong pin. Okay, so we've got t equals negative v naught plus or minus the square root v naught squared minus 2g delta y all over negative g. Sorry that I got a little close to the bottom there if that's hard to read. That's all over negative g. So now you've got two more negatives to complicate your problem. Delta y. Again, delta y and delta x isn't that big of a substitution. But those negatives can be the bane of your existence when you start mixing up, because now you've got three negatives to deal with. So I'm going to stick with the orange equations for the rest of the class. If you want to use the blue on your homework or on your take-home test or test, that's fine. But in your notes, I strongly recommend you stick with the orange as I use them, because if you try and flip-flop back and forth while we're trying to take notes and while you're trying to learn the concepts, it can get messy and cause added confusion that's unnecessary. Okay, that's the end of this video, but tomorrow we will go over part 2 of our blue free fall kinematics.